All right, so for our next, our next topic here, we finally found out in the last section what the radiation reaction force was. Now we get to talk about the mechanism behind it, and it is not intuitive at all until, of course, hindsight comes in. So this question is very long, but the answer is not too bad. But let's dive in. So deduce equation 100 from equation 99. Here there are three methods. A, use the 𝐬𝐵𝐸𝐺 formula to determine the radiation reaction on each end of the dumbbell. Add this to the interaction term in equation 99. All right, part B. Method A has the defect that it uses the 𝐬𝐵𝐸𝐺 formula, the very thing that we are trying to derive. To avoid this, let F of Q be the total D-independent part of the self-force on charge Q. Then F of Q is equal to F_int, interaction, plus 2F of Q divided by 2, where F_int is the interaction part in 99, and FQ divided by 2 is the self-force on each end. Now FQ must be proportional to F squared, since the field is proportional to Q and the force is QE. Okay. So FQ divided by 2 is equal to 1/4 FQ. Take it from there. Okay. That's just a scaling law. Smear, and then part C, smear out the charge along a strip of length L oriented perpendicular to the motion. The charge density then is lambda equal Q divided by L. Find the cumulative interaction force for all parts of the segment using equation 99 with the correspondence of Q divided by 2 goes to lambda d y1 at one end, and Q divided by 2 is equal to lambda dy2 at the other. Make sure you don't count the same pair twice. Okay, so let's not integrate over each other, or purposely integrate over each other and then divide by 2. That's what that's saying. Anyways, so for part A, find the 𝐬𝐵𝐸𝐺 from 𝐬𝐵𝐸𝐺. We find at each end, F end radiation is equal to mu Q over Q divided by 2 squared over 6 pi C A dot. And the interaction, F interaction of the radiation, is mu naught Q squared 12 pi C A dot. So, we have a 12 in the denominator versus 6. So the total radiation reaction is, you add the two together, F interaction plus the two ends, and you see that when we do that, we get 12 plus 2 with the Q squared over 2 goes to Q squared over 4, and you see that the 1/2, we factor out everything, mu naught Q squared 6 pi C, so I color coordinated everything. That leaves us with a factor of 1/2 plus the 2 factor from the formula plus the 1/4 from the Q over 2, and you see that all cancels to 1. So we are indeed in good form there. Part B, we want FQ equal F_int, F interaction of Q plus 2F of Q divided by 2. So for this, we just take that 2 times the 1/4, which we saw how we got the 1/4. And now we just add the two forces together. And so the 2 times 1/4 gives us a 1/2. So we minus the FQ to the other side to put like terms together. And we see that combines to 1/2 FQ equals F_int Q. So if that's the case, we solve that for FQ again, we just get a 2F interaction. And if that's the case, we take that 2 and divide and reduce that 12 to 6, and we get what we're looking for. For those confused, we split up a electron into 2 parts separated by distance d, and we have Q divided by 2 at 1/2 and Q divided by 2 at the other. So the total charge is still Q, but we just split up what the electron looks like in this model. All right, now for our next model, what we have is smearing the charge out. As you see in the diagram, we did that along the Y. So we have dy1, dy2. Velocity is perpendicular to that. And now we're just trying to set up an integral equation to, manipulate what we're looking for. So running the y2 integral up to y1 ensures that y1 is greater than y2, so we don't count the same pair twice. Alternatively, run both integrals from 0 to L, intentionally double counting, and divide the results by 2. Okay, so F radiation, we plug this in, run it twice. As you see the 2's there, run it through, and we cancel away what we can in the integral formulations, and we're good to go. Indeed, we get back to our original result that we were looking for. It's just up to us to be careful. Double counting allows us to divide through accordingly with the purple. And so, yeah, that worked really, really well, surprisingly. I'll let you look through the work for a moment, but for a hectic setup question, this is not too bad.